Hello everyone out there. Today we are going to discuss a topic that often comes in system design interviews. We're going to look how to design a checkout for flash sales whenever your Amazon Prime Day or Flipkart Big Billion Days are there and everyone at 12 a.m. in the night is trying to buy that one iPhone. How the system behind works. We'll go in depth and we'll see how engineers at Flipkart and Amazon are designing these systems to make sure that their website does not crash, they don't oversell, and the checkout works as smoothly as possible. Also, this is part one of a try series. In this series, I'm trying to cover different type of flash sales. This is about a product being sold. The part two is going to be about seat booking in a flash sale manner, like say Karan Aujla's concert, where millions of people are trying to get that one seat, and it is about really that one specific seat. In this case, however, in case of iPhone, it's not about that one iPhone. It can be any iPhone in the stock, right? So that's the difference, and that is going to be covered in the next video. And third video will be about the whole concept of virtual queues to manage traffic. So I hope you do subscribe and wait for those videos as well, so that when you go for an interview and you talk about flash sale, you just don't talk about the products, but in your mind you know everything. You know all different types of techniques and implementations for those specific use cases. So when interviewer is trying to throw curveballs at you, you exactly know what to answer. We will in this video try to cover all the different problems that engineers have found the solution to. And now after watching this video, you will know too. And even if you don't replicate the entire system design in your interview, if you are asked a difficult question, this video will make sure that you know the correct answer to it and you're not trying to memorize anything. All right, so let's start. So whenever there is an event like Amazon Prime Day or flash sales, uh, what happens? Generally, this is how the checkout page looks, right? There is a backend system holding 100 units, but this is what the user sees. And you do see a product page here, and you do see the title and the description, and there is an add to cart button here. Now, we're talking about millions of users hitting this page right now at this point in time. So the very basic thing is whatever is the non-changing data, the metadata about the product, let's just serve it through CDN, right? Done deal. There's no question about it. Whatever is non-changing, like description and title, just serve it through the CDN via a cached data is where a cache data is served to the users, and your database is not even touched here. Okay, so you're all good with this. Now let's focus our attention on this add to cart. At the moment any user clicks this, a backend call will happen, and the primarily it will be checking one thing, that whether the item can be added to cart or not, and if it can be added, will update the cart ID with that data, like that product will be added to the cart, right? So what is the information needed? The information needed is whether the stock is greater than zero or not. Okay, now do you need the entire stock amount? Do you need this 100 here, or do you just need to know that it is in stock, it is greater than zero? And do you reserve the product at just add to cart? Like, if I am able to add that product successfully in my cart, does that mean that I will get some reservation time to make that transaction? Nowadays, no. These are the answers that we have considered for this video. And no, you do not need exact stock count at the add to cart. You only need to know whether it's in stock or not. And do you reserve the product at just add to cart? No. First payment should win, because earlier when systems were like that, users were given time. Some of the users would just add to cart and not even make a payment, right? So that was the issue, and that is why nowadays almost all flash sales works on first payment first perspective, like principle. Now, why are these in form of questions? Because these are the follow-up questions you should be asking in your interview if you get to design this. This is the exact first question that should come to your mind, that you will ask to your interview, do I reserve or do I make it based on first payment? Because the entire design changes based on this, right? All right. So let's start with a very basic system. Anyone designing this would first make like this, that there is a user who is communicating to our system using an API gateway, where the APIs are getting hit first, which is internally routing to the product service. And the product service needs to know that for this product, what is the inventory like, whether it's in stock or not. So that is done by the inventory service here. All of the inventory stuff is being handled by the inventory service. This inventory service is having a database. Now imagine that at one point in time, millions of users are hitting, and this product service is checking with inventory service for each of those calls, and this inventory service for each of these calls is going to the database to get this data. You can understand how this is a nightmare. The database will not be able to handle so many requests, and the entire system will break down within seconds. So what is the fix? The most naive fix that comes to our mind is, uh, when one user asked for the inventory, just cache that information and return that as long as it's valid, right? That is the very basic principle of caching. Do not redo something that you just did. But there's a problem. The problem is, we're not dealing with something like product name that's not going to change often. We're dealing with something that is inventory count, and it's changing by the second. So let's see how that design would look like and what can be done, right? So this is how it would look like. There's a user hitting the same route and it's coming to the inventory service. Now, if we are writing to the database for any of the new inventory, like if there is a +1 or a -1, we'll just write it to the database, and in the background it will sync with the cache. So at times of reads, we'll just return from the cache. In paper this looks good, but what is the problem? The problem is this. What will happen is, suppose at T0 someone asked what is the stock, whether it's greater than 0 or not, and at T0 your database was having stock count as 0, but this information reached your cache a little late. At that time, it took this delta time to reach, because of which the cache already returned stale, because the read went to the cache and cache returned whatever it had, right? So this is a dirty read problem which is happening in this problem, like in this process, and that is why we can't use this. So what can we do now? The second best approach that comes to mind is, don't even use a cache. Don't use database as your primary source of truth. Use in-memory RAM. Now you'll say, are you seriously telling me that I am going to now store data in RAM? I would say yes. In this case, it's perfectly reasonable to store critical information like inventory stock for certain hot products in your services RAM. Why? Because you're not storing a lot of data, so your RAM can accommodate it. And this reading, like whenever this service reads from this RAM, it's a free call. When I say free call, I mean there is no network bandwidth required. So this is an order of one fetch, right? And there is nothing that can disturb this process. Uh, as long as this node is alive, this RAM will be alive and it will have the most latest data. But the other problem is, how do you make sure that one inventory service does not melt down because there are so many products and there are so many requests coming in, right? So you will say that I will load balance this and I'll add multiple instances. But when you add multiple instances, you can't have one instance dealing with iPhone 17 and another instance dealing with iPhone 17. When you're using RAM, one instance should take care of that entire product completely. Like if one instance is having iPhone 17 data, no other instance can have iPhone 17 data, and no other instance can modify it. So this is something that I'm talking about, that suppose your service is going to inventory, it's going to inventory's exact node that is having that data. How does that process work? When the request comes, it comes with the product ID. This service hashes the product ID and get the exact node number that it has to check with. Suppose iPhone 17 data is in this node, and this RAM will completely contain that data. This node will not contain iPhone 17 data, and if it does by any chance, then this system is bound to be corrupted, right? So that is one. The other is, you still see this is writing to a database. Why? For persistence. Why? Because this is ephemeral storage. The moment this node dies for any reason, all this data will be gone. Okay. So to store the data, for having real persistence, you will also write to database. Now you will ask that, when do I write to database? How often do I write to database? And how do I even write to database? So, and also before that, this is the information that you will be storing. You will be having a product ID and you will be having a quantity. So this is the sort of data structure that you can store in your RAM. This can look any way based on how you want to develop it, right? Now, let's see how you're going to actually persist this data. So you have couple approaches. The first is sync update to database. Like whenever you're doing this request, also do this at the same time and don't return until your database write is done. You can already see the problem with this. The problem with this is, say you have to go from 100 to 99 and you do this. Now this database is not sitting inside this service, right? It's outside. This is a network call. First, it can fail. Second, it can take a lot of time. So this will slow down. And remember, we are still hitting a million requests to this service and we are hitting a million requests to this service. But our database is not designed to handle million requests. That is the exact problem we started to solve, right? So definitely this is not even an option. You can't do sync updates to database. What can you do then? You can do async updates to the database. What do I mean by async update? It's like a fire and forget process. This RAM anyways have the latest data. It returned the latest data, but it also wants to persist it. To persist it, it will write that log, that entry, that action, that 100 becomes 99 to Kafka. This Kafka acts as a durable log. It takes up that responsibility to update the database in the backend, while this RAM or this node is not even working on it. It's the Kafka workers that are working on it. And this events that you publish here for say iPhone 17 topic, there you will store that what is the previous stock, what is the current stock, what is the timestamp, and what is the reason that the stock is changing. So you can have the entire history here. And now you will say, okay, I updated to this Kafka and all set. But what if this node dies, right? Some other node has to come up to take the load. When we do that, that node will not have any data from the start. It will not have what data is there here. This will be erased. Okay. So say node n takes up the responsibility of node 0 to serve up iPhone 17 at the time of failure for node 0. So what happens? It has to first figure out what is the current stock, then only it can start taking up requests, right? Before telling people how much is the stock left, it has to know how much is the stock left. Now you will tell me that just read from the database, take the last entry, but what if the Kafka is not done yet? Kafka has not finished writing all of these entries. So that is why this node at the time of its taking charge not just have to check with database, it also has to check with Kafka that whether it has something pending. How do we do that? We do this by replaying the events. Kafka can check the existing funnel and it can replay the events in times when we have to rebuild something from catastrophic failures. If database is not reachable, if something that in a case where neither the database is reachable, neither this old memory is available, at that time, these replays help. So we'll not go into much details about it, but I'm just trying to let you know that certain options are available. So when your interviewer tries to trick you, you can answer some of these things wherever applicable, right? If your interviewer asks, what if the node dies? First answer should be another leader node will be elected through a raft consensus process or any other sort of consensus process. And when that node takes the charge, it will rebuild the context. How does it do that? It will check whether the Kafka is up to date, it is done updating to database or not. And if not, then it will rebuild from the Kafka because that was the latest source of truth. Now, you will tell me that okay, all of this sounds good, but are you seriously telling me that engineers sitting in Amazon and Flipkart nowadays are writing uh, consensus algorithms or taking care of node dying and coming back up again just to make sure that the inventory stock is in the right state? I would say no. In current time, there are better ways available. What are those better ways? Is this. I will again go back to the concept of caching, but this time around, you will not be only reading from cache, you'll also be writing to cache. And this cache will not be an ordinary cache, it will be Redis. And the operations that you're going to use to write to those cache or to that Redis instance is going to be atomic operations like DECR and INCR, decrease and increase, rather than set and get. So this is an official documentation itself from Redis that suppose there are two clients and this is Redis instance and they're choosing the non-atomic approach where this client is trying to get the counter and it got 5, and this client is also trying to get the counter and it gets 5. Now this client tries to set the counter to 6 and this is also trying to set the counter to 6. Now the value is 6 because this guy was also trying to do a +1 and this guy was also trying to do a +1. So the final value that came was 6 and not 7. Ideally 5 plus 1 plus 1 should be 7. But the value that became final was 6. Why? Because both of them trying to set same thing. However, in atomic approach, you do an INCR here and you do an INCR here and done deal. Your correct value is 8 as it should be, right? So 6 plus 1 7 plus 1 8, done deal. So this is how Redis offers atomic operations that will not get mixed up. Like if there are multiple clients also doing asking for an increment, it will do it in the right manner and it will do it in the order it receives it. Okay, so some of these features are by default bundled and offered from Redis as a product. So the whole point is, if something is already done, why do engineers want to write it all again by themselves, handling so many edge cases? So that's not how real projects can ever work. The economics, the timeline, nothing will really work out if engineer starts to write everything from scratch. But why did I not bring this up earlier? Because if you go to your interviewer and the very first thing that you say is, I'll use a Redis with atomic DECR or INCR, he will not be impressed because you are kind of not even showing that you knew other approaches, you knew the older path, or you knew the conventional path. You directly jumped up to a fancy sophistication that he might not be appreciative of. He might want to know that if worst comes to worst, do you even know that something like your in-memory RAM as an storage can also be used? What are the problems that comes? What if the node dies? So all of those questions that we are trying to solve there, that is exactly what your interviewer would want to know, and that is why this was not brought up earlier, but now it's here. So now I'll add another set of complexities, another set of questions that I have here. One is, what happens when your Redis dies? First of all, can one single Redis instance take care of millions of products that Amazon serves? You would say probably no, right? So you're right. Your Redis will not have just one partition, it will have multiple partitions. But the same rule applies here, that one partition has to take care of the product entirely. That rule still applies. You can't have multiple Redis partitions take care of both the products. So you partition by product itself. So one product lives in one partition. One partition can take care of multiple products, but that product has to entirely live in that partition of Redis. So that is there. And another thing is that this Redis is still single source of truth. It is still writing and reading from here, but the persistence is still not there. So how do you persist? You again use Kafka to update your database. So your eventual persistence happens in database for all of the analytical purposes, but for your OLTP purposes, your transactional purposes, you're using Redis. Okay. Now now you will say that okay, one partition takes care of iPhone 17 entirely, but can it take care of millions of operations per second? The answer is yes. Based on the official documentations, the product can very well support extreme cases like flash sales easily in Redis. That is why it's used. That is why it is one of the most popular, and it can do it in order of one. Right? These operations are order of one, and they follow the order that they were asked in. So INs, like if first was this and second was this, that will happen in that order. That ordering is guaranteed within a single partition. When you try doing things in multiple partition, that's when this guarantee breaks, and that is why partitioning products by their product ID or whatever identifier is very, very important. Okay, now what is the final shape that you can propose to your interviewer when talking about this system? Okay, let's go over it one by one. I have also numbered the steps so that it's not confusing. So now there are millions of users. They're all hitting the API gateway, and first action that any user is going to do is add to cart, and they will hit the cart service. Now whenever you see these multiple boxes, it basically means it's a load balanced microservice with multiple instances running. Okay, so any of the fault tolerance and all of these are assumed here. Now the cart service will check whether the stock is there itself from the inventory service, and the inventory service will read from this Redis instance. Okay, and it will return that okay, the product is in stock. Now the person will place an order, so it will go to the order service. Okay, in order service, the first thing that we need to do again is just validate inventory. So we will validate the inventory by doing the same step again, that okay, see why, because people can add to cart a little later, like 10 minutes back, and while they click on place order, before we start collecting payment and all of that, it's a very good idea to once again check that the item is indeed is in stock, so that at least we don't take the payment and then say that oops, sorry, we checked 10 minutes back, and back at the time it was in stock. So for that reason, this step is important. Now the moment you made sure that yes, it's in stock as of now, you immediately go for make payment. How the payment service works is, it takes authorization from the bank that can I deduct this amount from this person's account, and it gets the authorization. Now the 7 steps happen, and make order goes to your product service. Now if there are 7 products or 8 products, it will go to one product service that will eventually check with the inventory service for all of those products and make sure that it does the DECR operation for all of those, update the stock, and then immediately return a success. And the payment service will then get the actual payment, and the final order service will mark it as payment received, it will mark it as complete, and it will return back to the user that your order was successful. What's happening here is, after you did your atomic operation, this 10th step happens asynchronously in background to go and update your database that yes, this product has like decreased in stock by so and so amount. So this is how you're able to serve millions of requests all at once without breaking your system. And if I had come to this directly, some of these things would have looked very obvious. But I wanted to build that thought process, that how can we arrive here, right? So I hope this was interesting. I've tried to keep it simple. Some of these authorization and payment things, I'm not getting into much details, but you can drop in a question that you have around this, and I will try to answer that. And I will try to link some of the documentations about Redis in this video, so that you can go and read about those atomic operations and how they are so superior. And be tuned for the second and third part of this series, where we will see how, when users try to book a very fixed asset, that 1B row of a concert or a comedy show, that seat we can't give it to anyone else in that window. So that guy needs a reservation, and for reservation, a whole new row locking, some sort of a DB locking, some sort of a strategy comes in, and I'll go deep into that right after I upload this one. So do stay tuned for that. All right. Thank you so much. See you next time.